Okay, so yeah, so apparently the video I recorded didn't really record very well. So we're gonna go over aspects of friction from that video and then do some practice problems and kind of work our way up to harder and harder problems so that it's handle whatever. There's Charles, all right. The friction can be a little tricky because it's not like the force of gravity, which is always just minus mg, always, just all the time. It's always a constant. With friction, the actual formula you would use is kind of case dependent. It kind of, the way you handle friction, you have to kind of evaluate the situation and figure it out from there. For people who about the internet. All right. So, what you guys do, if you're at home, I don't know, hopefully you can push something around, push your computer. If you're here, I'm going to hand out some books or something to push. All right. That, and I don't know, if you have, different things to push. Okay. So there, 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 I choose something else. Okay, so so as you're pushing things, take a second to do that because this is the key. I don't know if I want to try to understand. Okay, tip this down so you guys can see. Okay, so here I've got a book. I push a little bit. I push a little bit. Nothing's happening. Push a little harder, and then it goes. Okay. So go ahead and see if you take a second to do that. Just kind of start with a little push and just gradually ramp it up. Okay, so what do you notice about this? What happens when it starts to slip? Do you notice a change? Is it different somehow? Think about the pressure on your finger. Is it? It's easier once you start. It gets easier. Do you notice that there's that like slip, and then it's kind of easier after it's going. So try again. Now think and feel. Look for that effect. Where you push, and once it goes, it should be easier to keep it going. Can you get a sense for that? How it sort of drops in the difficulty. Okay. Another thing to think about. Stack them up. So I gave you guys different books. Try one book versus two books, and I'll just go crazy. I'll do notes for thermo and physics, and we have some astronomy in here. Just go it all in. Okay. Okay. Now let's kind of think about what happens. I push a little bit, nothing happens. Push a little bit more, nothing happens. In fact, it takes a lot more effort to even get it started. So we call it impending motion. It's about to happen, like impending doom. Okay, impending motion. All right, people at home, I'm really sorry. The Wi-Fi is in and out, so bear with me. I'm trying to record it. So assuming that it really does record, then I will post whatever I have, but I don't know what else. I can't really do much else about that. All right, so what we notice is, what are we seeing here? What's the difference? It's harder to get it going, and even once I get it going, it's harder to keep it going. What have I changed? What have I changed? There's more mass. Is it the mass that's important? Okay, well, let's think about it. Well, that's what I want you to think about. Is it, what does it depend upon? Okay. So, first of all, what is friction? It opposes, it's a force which opposes motion. It's kind of a resistive force. So friction is a force that opposes motion. The symbol I will use for friction is a kind of a script F. Sometimes people write a capital F with the word friction underneath. That just takes too long. There's nothing wrong with doing that. It's just I'm lazy. Okay, so in general, I'm just generally talking about friction. I'll call it script F. It's a force. Units are newtons, same as other cases. And okay, it points. Let's think about it. If I push to the right, which way is friction acting? So if I'm pushing to the right, the friction force, which counteracts my hand, is going to be going in the opposite direction. So if I push to the right, it acts to the left. If I push to the left, it acts to the right. Okay, so it's opposes. That's why it's resistant, right? What that also means is that when it comes time to do math, we want to come up with maybe sometimes we can even get a bit of a formula for friction, but it's not going to be everything because it's context dependent. And that happens a lot with friction, right? To write down a formula for friction, that formula would have to know about my finger because the way I apply the force changes the answer. Well, there's no way we're going to be able to come up with a mathematical formula to describe people and cars and the world, like all the details of the world. So some of it, you just have to look at the scenario, look at the picture, and then just put in the minus sign by inspection. Sometimes you just don't know. Right? I mean, you can't just like have a general formula always. All right, so there's that. That's one thing. The friction force acts, it resists motion, and acts along the surface of contact. Okay, so it points along the surface. So it's surface of contact. If two surfaces or two objects don't touch, there will be no friction force between them. So you have to have contact to have friction. All right. Okay. Somebody else here. Okay. So here's what we noticed experimentally when we kind of push things around, is we have the following kind of situation. Okay, this on this side, this is the force from my finger, the force I'm pushing with, the force applied from the outside. The size of the force that's being applied. Over here, we're going to put the friction force. Now, really, I'm being honest, I'm talking about the magnitude of the friction force, but when people draw this chart, they never put that there. We've already talked about the minus sign, the direction of it. that's case dependent. You have to look at it to get the minus sign. So I'm just talking about the size of the friction force. You have to look at the picture to figure out which way it goes. Okay? Okay, so if I push none at all, how much does friction need to supply to resist my zero force? So if I apply nothing, I push up above nothing, how much resistance will friction generate? Zero, right? If I don't apply a force horizontally, then friction doesn't need to do anything to oppose it because nothing was applied, therefore there'll be none generated. It's lazy, it only does what it needs to. So if I apply, let me change colors here. If I do this in red, tell me if you guys can see this on the computer. Can you see the red dot? Is that okay, or is it too faint? Can you give me a thumbs up if it's okay? Let's see. Okay, there's one. All right, got a thumbs up. Okay. Now, if I apply a little bit of force, how much friction force is needed to oppose it? If I apply a little bit, friction just applies a little bit to cancel it out. So a little bit of force, a little bit of friction. A little bit, a little bit. In fact, it's 1 to 1. If you drew these with the right scale, it would have slope 1. What would happen if I put in 1 Newton of force and friction generated 2 newtons of force? If I put in 1 and friction generated 2, what would happen to the object? Yeah, I would push this way, it would spontaneously pop back. I think there's like some comic book where there's like a villain who does something like that, where if you hit him, then it rebounds twice as much the other way, or something like that. All right. I don't know what that world would look like because I don't live there. Okay, that doesn't happen. Right? You would have all sorts of stability problems. You would like push a little bit and it would blow the one way and run into something, and it would blow even farther, faster the other way, and just explode. Things would go out of control. So it wouldn't be a stable universe. Anyway, that isn't what happens. So you get equal and opposite here. Not Newton's third law, but just the friction force does exactly what it needs to do to keep things still. It doesn't want motion. Okay? Increase, increase, increase. That's what happens. Now, eventually, I win because I've got ripped physics muscles, and that's what happens when you do physics. I don't think Charles believes me. All right, so I push harder, I push harder, I push harder. Friction increases to compensate, increases to compensate, increases to compensate. But because I'm, pretty tough, eventually the situation changes and motion starts to occur. Okay, so there's a point here. And what I would say is this is the point right before it slips. Okay, this is going to be the point where its motion is impending. Impending motion. It's just about ready to slip. All right. And what happened to the friction force, or the force we felt kind of resisting our finger after it started to slide? What did you guys tell me? It got easier. It was easier to push things. Yeah. So it turns out, in real life, it's kind of complicated. But what we're going to do is kind of simplify the story, and we're going to say blue. what we're going to say, we're going to say it's going to drop down, and it becomes, it's a good approximation constant. Now, in reality, it's a little bit more irregular. And in this region, this is quite complicated, okay? But it's very narrow, and so basically, we will not talk about this at all. We'll just ignore this detail. Engineers, like mechanical engineers, would have to learn about that. Okay. So, in red, the red portion, that was before motion happened. So everything was static, stationary. We call this static friction. So this region is static. And so in this region, we will write F with a subscript, S. I mean, it's all friction, but clearly, this is just qualitatively different than this, just looking at the shape. It's just different. So, all right. Over here, it is moving. We're going to say the situation is kinetic. It's moving. So we're going to have kinetic friction. And the symbol we will use is F with some K for kinetic. Okay, let me check to make sure it's visible. Is that visible to everyone on the internet? Yes? Okay. Sometimes when I change colors, people struggle, so I want to make sure. Is that okay? All right. So to study friction problems, you have to kind of understand this diagram. This is complicated, right? Looks like this, it's got some weirdness. Looks like this. And so when you look at a situation kind of with friction, the first thing you want to do is figure out where you are on this diagram. Is it static and here, or is it sliding and over here? And sometimes you're just told, oh, it's moving. If it's sliding, if the problem tells you that, well, then immediately you know you're over here. That turns out to be the easiest case. If it doesn't tell you, a lot of times the problems will be blah, 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 something's happening. First, figure out if it's going to remain stationary, right? So say it starts at rest. So you want to figure out, oh, okay, am I over here? Or you want to figure out, is it at rest, but the force applied is more than the maximum possible friction force? Because friction can only go up to here. Static friction can only go up to here and no higher. So you want to look at the force applied and compare it to basically this number, the maximum friction, static friction that's possible. That will determine if it's going to start moving. That's really what happens. So you look at what is the maximum possible static friction, compare that to what you are applying to the object, and that tells you if it's going to remain stationary or if it's going to start to move. And then once it's moving, it's kinetic friction. So that's sort of this bit of a logic puzzle sort of thing where you have to decide where you are on this thing. Okay, in this region, it's really complicated, and it's not a straight line or anything natural, really. You guys can see this. So, all right, we'll wipe the table down. If you kind of make your fingers a little bit moist, and then for people online, I'll try to do this on the computer and listen to it. So push down really hard. So you're trying to maximize static friction. It turns out to get the most static friction you can, and then push it forward. What do you feel or what do you hear? Okay, here you go. Online, I think you'll be able to hear this. Can you hear that sound? What did it sound like? Charles, be polite. No comment. All right, I'll try it again. Can you hear that stutter? Okay. Excuse you, Charles. I don't know why I always pick on him, because he never says anything. That's the thing. All right. Anyways, it's not a duck. No flatulence involved. What's happening is it's something called slip stick. And what's really happening is you're here, you surpass this, it starts to move, but your finger doesn't quite keep up, so it becomes static. Then you increase back to here. So it's like it's complicated dance between slip stick, slip stick, slip stick, slip stick. That's what makes that stutter kind of sound. That's what happens when like if you have chalkboards and they squeal. I think that's what's happening, right? Because it's all about, you want to basically get away from this point. You want to get over here where it just slides, and then there's no problem, there's no sound. But if you're like right at the right spot, it makes an awful sound. I think that's what's happening. Okay, so that's slip stick. We will not touch that at all. That's really complicated to kind of work that out. All right. Now, so everybody conceptually okay with this? That's a nice story. We want to be able to solve problems quantitatively. We need to mathematize this graph, and that's what we do. So first thing we have to do is kind of guess or kind of figure out what are the possible variables. Well, first of all, the first thing we do is figure out what part of this graph do we have any chance to try to guess what the formula is. And then when we figure out what we even have a chance to model mathematically, we will kind of talk about the relevant variables and we'll know the formulas. Okay. Here, in this region here, this red region, what do I know about the friction force here when it's static? Friction force has to equal what? It's not moving. So if I push a little bit, and that's it. I can't really say anything other than that. And since there's no way I'm going to be able to model and write down a formula for my hand, it's too complicated. There's no way you can come up with a better formula about this. You're really just going to say static friction does whatever it takes to make things stay still. Done. There's no other deeper formula. Okay? It just turns out. Now, it turns out more, and it becomes a little bit more. So as I add more object, as I make it bigger, in some sense, it gets harder and harder. So as you add more and more, in my case, books, this blue point gets higher and higher and higher and higher and higher. The threshold for motion gets higher and higher and higher. Okay? That is the thing I want you to see. And similarly, the more books you have, the harder it is to keep it going. So both this blue dot and also this green portion get taller when you somehow increase the number of books in this situation. Okay, so it turns out we can mathematize that. So let's kind of guess. What are the relevant variables? What is increasing? What's the important thing that increases as I add an extra book? It could be that I'm increasing the mass. You could say it that way, because I am. It could be that you're increasing the weight. Maybe it's the weight that matters, because I am. It could be that something else is increasing. So how do you figure it out? Well, try to imagine situations where you have mass, but you have no friction. So then that tells you that it can't be mass that directly controls friction. Well, you know, your mass is intrinsic. You always have mass. But if you, but on the other hand, if I step on a concrete floor, or this floor versus ice, the friction is very different, but my mass didn't change. So it's probably not going to be mass directly that controls friction. In an indirect way, yes, but not in the formula, the variable that enters won't just be mass. Because the mass, you know, if I'm standing next to the frozen pond and then I step onto the frozen pond, my mass didn't change, but clearly the friction did. So it won't be mass. Same with weight. If I'm stepping onto a frozen pond, my weight doesn't change. Okay, so that won't be there. Now, what does change when I step from this bank to the ice? What changes in that case? If you touch the grass or frozen grass, frosty grass, and you touch the frozen ice, what do you notice? What does change there? The surface, right? The roughness. There's something different. Okay? So friction in both of these will depend upon, so we'll say F sub S maximum, which is the height of this blue dot. That's the max. And the kinetic friction depend on the surface, the roughness. Okay, so clearly there are different kinds of surfaces, and it actually depends upon both the surface of the object and the surface of the it's on top of. So, you know, it's really a function of both materials. So you could have steel on steel, aluminum on aluminum, glass on steel, rubber on ice. Okay, the details matter. Okay, so that's one thing. So the surface is important. Let's think about this. Can you imagine a situation where you have minimal weight, but you could possibly still have friction? Velcro. Okay. Yes. All right. That is an option. I meant you personally. Where could you go so that your weight was minimal, but you could have friction, which does tie into Velcro? Where do you have to go to make your weight much smaller? Right? You're up in a space station. Your weight it's not zero, but it's much smaller. But you know, astronauts can slide their hand and have friction against things. Yeah? Or even simpler. You could have a situation where you have this tin of putty, right? So there's friction here as I push on it. But when I go this way, this object still has a weight, and it's still the same surface, but the friction force is essentially zero. So it has a weight. It's the same surface. It's not a surface effect, but the friction force is zero. What's changed? What force has changed as I change the angle? It's the normal force. When you hold it vertically, the normal force, if it's really vertical, would be zero or essentially zero. Whereas here, the normal force is equal and opposite the weight. It's equal to weight magnitude. So that's kind of our hint. By imagining different situations, either a space station where there's no weight, but you can have friction, or tipping something on the side where you still have a weight, but you have no friction, you kind of deduce that it's not the weight that gives you the friction force, it's the normal force. is the normal force. So, depends on the details of the surface and depend on the normal force. And really it's the magnitude of the normal force. Right? Depends on the magnitude of the normal force. So the formula, okay, so we have the following formula. The maximum static friction value, so that'd be the blue dot up there. Okay, its magnitude of the maximum value static friction for a given object in a given scenario equals times the normal force, and again, this should really be magnitudes, although I will tell you when I use it, a lot of times I drop the absolute values just because I'm lazy. But it's the magnitude. The direction of it, you have to look at the picture. So these are all formulas for magnitudes of things. You have to look at the picture to get the minus signs right. Okay, this thing out front, what is this symbol? What is this symbol? It's a Greek letter. What is it? Mu. Very good. Greek letter mu is most definitely not a mu. Okay? When people spell it out, they write it as M-U. It's a Greek letter. Mu, not moo. We're not cows. No cows. Okay? You say moo, everyone laughs at you. Even if they don't, if they're too polite to do it out loud in their mind. Right. So this is mu sub s. This is the coefficient of static friction. What it tells you is the roughness, basically. So two surfaces which have a lot of friction, tend to be very rough. That's this number. Okay, it can't be negative, so mu sub s is going to be, it'll be bigger than 0 for all real objects. And okay, I don't know of any upper bound. I mean, there's no reason it couldn't go up to 100, I guess. Except, to be honest, once you get it's I think for any real situation, it's less than 1. If you get 1,000 as your answer, you probably did something wrong. If you get to a coefficient of static friction, which is 1,000, probably thinking of it as like two objects that are dry, that are resisting motion, it's probably not the right way to think of it. It's either you should think of it as more like something soaked in concrete or something like that. I mean, it's just a different kind of paradigm the way you think about the problem. So if you need to model something with an insanely large mu value, then probably it's not really friction anymore. You should think of it as like glue or cement or I don't know what. But anyway. So this number will be typically between 0 and really typically it's between 0 and 0.5. I think aluminum on aluminum, that tends to have a lot of friction because aluminum is a soft metal. It tends to kind of rub and dig into itself. I think this number is like 0.5 for aluminum and aluminum. That's a lot. I think standing on ice, which would be a small number, is like 0.12. So that's kind of the range of what we experience. I'm not going to say there's nothing more than that, but those are kind of typical numbers. 0.3 is a very common kind of number. All right, great. That was static friction. That's the blue dot, impending motion. F sub k, Again, I should write magnitudes, but I'm lazy. Oh, before I do that, this is just the blue dot, right? Because it's the maximum value. If you look around on the internet or in the book or whatever, sometimes they write this as F sub S, not the maximum value, the whole red and blue part. They'll say the magnitude of that is less than or equal to mu sub S times the normal force. It's really saying the same thing, right? That you can't really say anything in detail about the red portion of the graph up there, but I do know that it's less than the blue dot. So that's all that's really saying. It's really the same information. Okay. All right. All right. Then on the other hand, once you know it's sliding, when it's kinetic friction, that's just a horizontal line. It's just a constant, independent of the velocity or the acceleration or anything else. It doesn't matter. It's a constant. Once you know it's moving, it's sliding, that F sub k is just a constant value. And again, it depends upon the surface and the normal force. So it's not maybe hopefully too surprising that it's not this, mu sub k times the normal force. And this is the coefficient of kinetic friction. Okay. Coefficient of kinetic friction. Now, what do you think? Can you tell me something from that graph about what you expect in terms of the size of the coefficient of static friction versus the size of the coefficient of kinetic friction? So you're given, here are these books. The normal force doesn't change, right? It's going to be what it is. Same normal force. I push, I push, I push, I push. And we all agreed it got easier once you got it moving. So the kinetic friction was smaller than the static friction, the maximum static friction. That's the key, maximum static friction. So that means, okay, maximum static friction was bigger than kinetic friction, but the normal forces didn't change. It was the same stack of books. So therefore, mu sub S should be bigger than mu sub K. And that's typically true. Again, I don't know if it's a hard and fast like law of nature, but typically, the static friction is bigger than mu sub K. So for example, for H2O, for ice, solid water. So for typical objects on ice, mu sub S is like 0.12, and mu sub K is like 0.08, something like that. So it's about a third less. I think that's pretty typical. Aluminum has a lot of friction. So mu sub S is about 0.5. But the other thing that's striking about aluminum, has anybody ever had to like slide like pieces of aluminum? Like, I don't know. All right. What you notice when you do that is it kind of digs into itself because it's so soft. And it doesn't get easier when you make it move. It stays hard even as you drag it. So it turns out for aluminum, they're both about the same. There's a little difference probably, but they're about the same. So that's kind of an unusual sort of thing. For almost all other normal things, there's at least some drop when you go from static to kinetic. Okay? This is the content, more or less, of that first video that was no good on YouTube. Let's take, say like 4 minutes here, regroup. Then we're going to use these ideas to solve problems. And we'll just practice, 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 practice. Okay? People online, you doing okay? All right. Brielle, you doing okay? Can't really see. All right. All right. I will. We're going. I'll pause recording here, and then we will. All right. Let's imagine we have a table, and on it there is a box. Just for definiteness, let's give it a mass. Let's say 5 kilograms. Mass is 5 kilograms. So what I'm going to do is take this scenario and just kind of add more and more bells and whistles to it, and we'll figure out how things behave. So let's do 2 things. Let's imagine we pull with 20 newtons of force on a rope. Okay. And the first thing I want to do is imagine there's no friction. So let's figure out what is the acceleration of the box, and we know it's going to go to the right. It's in the x direction. Okay. So what's the acceleration of the box in this case? I did an example like this in the second video, but I don't know if everybody watched it. So let's do that. Okay, so take a second. Let's work it out. Okay. How do you solve a problem like this? Well, step 1 is to assess what forces are relevant. And step 2 is to construct a free body diagram. So it's a force problem. You know there's going to be a free body diagram in there. So make sure to just dive into doing that. So we want to find the acceleration, which we know is going to be in the x direction, horizontal. That's the goal. Right. So take a second and do that. Sorry about that. I was supposed to have you guys make the force table. Did you guys do that? Mumble, maybe. All right. So you guys are supposed to do that. I'll make you guys do it first next time. But step 1, identify the forces. Step 2, draw the diagram. Step 3, somehow find all the components of all the forces and identify the x pieces and the y pieces. I like to do this table. You can do x hat, y hat, unit vectors. It doesn't matter because it's all amounts to the same thing. All right, so we get our force table. Then I want to find the net force. So the net force is the sum of all the forces. So that just means I add up all the forces. So I want to find the net force in the x direction. I add up all these forces. Well, there's just one, 20 newtons. So the net force in the x direction is 20 newtons. And I add these up. The net force in the y direction is going to be normal force minus mg. Okay? Is that all right? So far, we're not actually doing any physics. This is just math. Just, drawing arrows and doing mathematics of vectors. Okay, let's hope that doesn't fall. Physics comes into this when we say the net force equals the mass times acceleration. So that means F net x equals the mass times acceleration in the x direction, and F net y is the mass times the acceleration in the y direction. Okay, this number, that's what I get by adding these up. That's 20 newtons. That equals the mass times the acceleration. The mass was 5. Okay, so that's the acceleration in the x direction. From this equation, what do I do with this one? I have a formula for the net force in the y direction. Okay, that's fine. So I have a formula here. Can I say anything else about this equation? Do I know anything about the acceleration in the y direction? Is the box moving in the y direction? No. So it's you know, it's not like Dukes of Hazzard or Peter Pan or something. It can't fly. So there's no motion vertically in this problem ever. So the acceleration in the y direction is just 0. So I know that this number is 0. And, okay, so now I can turn that around to say the normal force minus mg equals 0, or normal force equals mg. Plug in numbers and 49. Start again. Something like that. Okay? That's the process. All right. Everybody okay with this setup? Okay. I'm going to go ahead and write these formulas down here, up here. F sub s max equals mu s times the normal force, and F sub k equals mu k times the normal force. Okay. I'm going to put those on the board. Okay. Same scenario, but we're going to add in friction. Same scenario, but add in friction. And I'm just going to make up numbers here. Oh. Son of a gun. Right, that was 20 newtons. Yeah. Okay, so 20 newtons. Okay. Now, let's assume mu sub k equals, oh man, let's assume mu sub k equals 0.15, and assume mu sub s equals 0.2. All right. So let's imagine it starts out at rest. Okay, it starts out at rest. So assume the initial is 0. Okay. Now, same basic situation, but now we've included friction. So if we've included friction now, the first thing we want to know is it going to remain at rest? Yes or no? If the answer is yes, well, then that's the end. If the answer is no, you could imagine starts to move, and then after it starts to move, what will the acceleration be? Okay. Okay. Does it remain at rest? And if no, what is the acceleration in the x direction? Okay. So how will you do this one? Here's how I would do this. So it's this complicated graph, right? You got to figure out what you're doing here. So what I would do is the following. I would work out and say, assume the answer is yes. Assume it remains at S for a moment, hypothetically. Because you got to figure out, basically you're going to use the guess and check. You're going to guess that it's still in the red part. Just guess. And then check, though, that the number for friction that you need to make that true doesn't pass the blue dot. So I would do it where I'd say, assume that it stays stationary. Assume static friction. Assume the friction is static. So figure out what number of that friction force would have to be. What should it be? Okay. That says that if friction can provide that force, it remains at rest. But then you have to compare that to the maximum possible static friction. And then that's going to determine, you made an assumption, you checked, is it valid? If the answer is no, then you know the assumption was wrong. And then you know it's going to start sliding. That's how I would kind of feel my way through that scenario. There's not the only way to phrase it, but there's always some sort of a guess and check, no matter how you phrase it. Okay? Some people in high school they do something like they assume friction is maximized, and then there's something where you get an acceleration that's negative, or something. There's something about a minus sign, and that acceleration they interpret as an indication that it wasn't possible. Something I never understand that logic, but so I think. Anyways, I would do it the way I said. I would assume the answer is yes, static friction wins, but then I have to check that, and if it fails, then I go to the kinetic case. All right. Regardless, what's step one for solving this problem with forces? This problem with forces. What's step one going to be? It's the first thing you do for any problem with forces. Identify the forces and make a free body diagram. Okay. Even if the problem doesn't tell you to do that, do that. It's just bookkeeping, more or less. But if you don't get the bookkeeping right, it's just wrong from the start. And I'm always on any force problem. I look for partial credit, so it's like, oh, did it do that? Oh, partial credit, got it. All right. Okay, give me a thumbs up when you have a free body diagram. People online, just a warning, it's telling me my internet connection is unstable, so hopefully it doesn't cut out, but just so you know, it could be coming. All right. You have a free body diagram? Thumbs up if you got it. Yes, yes, yes. Online, Charles, do you have a free body diagram? Rose, I can't see motion. All right, let's go through it. The forces are very similar to before. There's a weight, there's a tension force, there's a normal force, but now there's a resistive friction force. So the new part is over here, some friction force. I don't know if it's static or not, so I'll just call it in. I'm going to assume it's static for the purpose of solving the problem, but I don't really know. Okay? After I have my free body diagram, my force diagram, what's the next thing I need to do? I have to work out the net force. You can do it with components, x hat, y hat, I hat, j hat, however you do it, or I would recommend making a force table because it makes it really clear if you've got it all included. Just take a second and do that, and I'll do it on the board. Force table here. So if I was constructing a force table, I'd say I got forces x and y. Oh, I'm going to choose x and y the same way I did before because nothing's rotated. So I had weight, normal force, tension, and now I have friction force. Okay. And I'm going to, so the weight is only in the y direction, minus mg. The normal force is only in the x direction. The tension is still 20 newtons in the x direction, nothing in the y direction. Which way does the friction force point? Well, it's only to the left. So now, I don't know what the friction is. I don't really know whether it's static, kinetic, maximum static. I don't know. It could be any of them. I'm going to assume it's static and figure out what value of static friction would hold the thing at rest. But then I have to check and compare that to the actual value for the maximum possible static friction. So I'm going to just assume it's static for a minute. That's my assumption. So I'm going to assume static. Then compare result to max static. So I compare f sub s, is it less than or equal to, question mark, f sub s max, right? If it fails this, then I know my initial assumption was wrong, and I have to go back and resolve, but you just don't know. Whenever you have graphs that are kind of piecewise like that, where you have guesses and checks and zigs and zags, or sorry, when you have zigzag kinds of graphs, when you solve problems using it, it means you have to do some guessing and checking. It's not just continuous. Okay, but I do know that there's no friction in the y direction. You know that much. All right. Did anything change with the normal force? No, it's exactly the same as before. Therefore, just as before, I know the normal force equals mg, which is like 49, whatever, something like that. You can. Now, what about this one? We are assuming that it's static. If it's static, what's the acceleration in the x direction? 0. So we're going to assume it's static, and that would tell me that 20, just to be careful here, the minus signs have to be watched. I'm going to say that since it goes to the left, I'm going to put a minus in there. So I'm going to say 20 minus f sub s is the net force. That needs to equal 0. Therefore, this would tell me if it is static, F sub s is 20 newtons. Okay? If it remains static, the friction force is 20 newtons. That makes sense because I push with 20 to the pull with 20 to the right. The friction to keep it static, you have to have 20 going to the left. Oh, yeah, all right, that's fine. And the minus sign tells me it was going to the left here. If you want to make this some people prefer to put a plus sign here. That's okay. That becomes a plus, and then you would actually get an explicit minus sign there. It amounts, as long as you have the picture, it's okay. You know what to do. You know how you interpret it. All right. Now, how do I know? Is that going to be allowed or not? What's the next thing? I want to compare this result with the maximum possible static friction. Okay. Well, the maximum possible static friction, I kind of want to save those numbers. I don't want to erase that. So I'm going to come over here. Yes. The maximum possible static friction let's work that out. F sub s maximum equals mu sub s times the normal force. But mu sub s is 0.2, and the normal force is 49. So if you multiply that out, that's going to be a little less than 10. 9.9 or something. 9.8. Okay. Oh, that makes sense. Yeah. Okay. So that's some number. How do I interpret that? What does that mean? Remember, at this point, people get lost in the problem a lot of times. So you got to regroup and think, okay, what was I even doing with this stuff? The goal was to make this comparison. We don't know that it's actually static friction. We just guessed. We have to check that. So what we said is, if it's static, I need this to be 20 newtons. But the maximum possible static friction is 9.8. So you're never going to get 20 newtons of static friction. Therefore, what? It's going to move. Yeah. Motion is you've asked the friction to do more than it can. Static friction to do more than it can. It is going to slide. Okay. So it's going to slide. So that means you did a great job. So I want to compliment you guys. You guys did great. But all this was a wrong guess, and so therefore it's all irrelevant. You got to do it all again. Okay? So now, all right, it's not static friction, so that's all wrong. So it's going to be kinetic friction. All right, well, okay, free body diagram. Well, guess what? It's not always. The diagram is basically the same. You just happen to know that it's kinetic friction. So you want to make a new force table for assuming it's kinetic friction. You have to resolve it all. But when it's kinetic friction, now we don't have to just leave this as an unknown. We have an actual formula for kinetic friction. So you can go ahead and put in your formula. So the formula, well, it's going to be minus because it was to the left. And it was mu k times the normal force. Okay. Right? Because it's kinetic friction. We know mu k. Nothing changes on the y component, so we know the normal force is still 49. So we can work this out. Okay, so let's do that. So this is going to be, So over here, the y part is the same. This one is going to be 20 minus 0.15 times the normal force, which is 49 newtons. Does anybody have a number for that? 20 minus 0.15 times. Oh, so it's 7.5. So it's going to be 12.5. That's about right. 12.6. Okay. And all of this is wrong. But it was the right logic. It just happened to not be sufficient. Okay. So we learn, F net in the x direction is 12.6 newtons. Is that okay? Last time we set it equal to 0. Is that okay? Or did we make a mistake? Well, why did we set this equal to 0 last time? That was because we assumed it was static. But we didn't know that that was true. It turns out it wasn't going to be true. The assumption was invalidated. So once you give up static, there's no reason that this should add up to 0 anymore. It might accelerate, it might not. I don't know. It is what it is. It's this. So apparently it's not. There is an acceleration. That's just the answer. Okay? So that's the net force in the x direction. The goal is to find the acceleration. So I'd say 12.6 newtons equals the mass, which was 5 kilograms, times the acceleration in the x direction. And I get the acceleration in the x direction is 2.5. I'm doing that right? You get that right? Round numbers. I'm estimating because I'm doing stuff in my head. But and then look what happens. Does it make sense? That's always the important thing. Because we have to make all these weird assumptions and check and guess and check. Okay, the answer we get is 2.5 meters per second with friction. With no friction, we had 4. It makes sense that friction is going to slow things down. So, I mean, I don't know what the answer should be, but it feels right. It's within the realm of possibility. All right, how do we feel? I always ask you guys to rank things. 1 being, no bueno, no good. 10 being, I could write the textbook, piece of cake. How many people feel like they're in the kind of 1 to 3 range? All right. How many people are in the 4 to 6 range? Kind of, maybe you can follow along, but you struggle to do it on your own. Is that? And how many people feel like they're in kind of the 7 to 10 range? They can do, on the easier ones, they can do it, maybe some of them might throw them. Yeah. Okay. All right, bit of a mix. The process, the flow of it is always the same. Always the same. Things that can complicate our lives are things like your obnoxious younger brother puts something under the table. So now it's tipped. And you have to solve the same problem. We'll go ahead and say you're pulling up the rope or up the ramp or table with 20 newtons. Just keep the numbers the same. And let's go ahead and, we'll say it's really tipped like crazy. So let's assume it's actually tipped up at, let's do something with nice, easy trig. So let's do 30 degrees, which would be insane. But I just do that because then I use 30, 60, 90 triangles. There's nothing special about that. Okay, so I'm going to assume it is tipped 30 degrees. You don't have to do 30. 30 degrees. Whew. Okay. I want to know, is it going to slip? Just assume it starts at rest. Does it slip? Yes or no? If the answer is no, if it's going to move, find the acceleration. Does it slip? Yes or no? If the answer is no, find the acceleration. Now this one's tricky because there's trigonometry, so I want to help you with that in a minute. But first, what's step one? Step one is construct free body diagram. So get that done first. Free body diagram. We'll erase this. Construct a free body diagram. Okay, so the free body diagram, it's kind of similar. There are some changes. Gravity, weight, always goes straight towards the surface of the Earth. Actually goes to the center of the Earth. Which way does the tension force point now? Well, it's the strain or whatever it is parallel to the table. So it's going to be tipped up 30 degrees above the horizon. 30 degrees above the horizon. So the tension force is now up at 30 degrees. Okay. What else do I know? What about the normal force? Which way does it point? Normal means perpendicular. So the normal force is going to be perpendicular to the table. So the normal force is going to go this way. Ooh. Okay. Let's think about that for 1 second. So if this force is up 30, that means, and they're always perpendicular, so that means this angle is 30 degrees. Okay? The tension and normal force are like it's a right angles apart. So if I tip it up 30 degrees, they move together. Okay? Okay. And what about friction? Well, we don't know. Let me think about this for a second here. Because gravity is going to effectively pull it down the ramp. The tension is going to pull it up the ramp. And we don't know about the static friction. So let's just make a guess. And then if our answer comes out, say positive, then our guess was right. And if it comes out negative, our guess was wrong. Something like that. All right. So we'll just make a guess and go from there. So let's make a guess that friction points this way. And the numbers are going to tell us whether we were right or not. But we do know it has to be parallel to the table. Do you guys understand that friction could point up the ramp? You thought about that? Think about this one, right? Oh, sorry. This book is on a downward slope. Friction is holding it uphill. If I replace this binder with ice, the book's going down. So therefore, friction is going uphill. On the other hand, if I were to start to try to pull it, I try to pull it up the hill, then friction's repulsing that, so friction's actually going downhill. So friction does, that's why it's tricky to figure out which way friction is going. So sometimes you just make a guess, and you have to check or solve it, see if it's possible. There's not really a better way. So I'm going to make a guess that's going this way. We'll find out. I don't know. And I'm only guessing this because I'm imagining that this is what I'm actually doing. I'm pulling it uphill, so friction's. But I don't know. Okay. Now, if you had no friction and no string, which way would it accelerate? Is it gonna move? Is the box going to move this direction on this kind of diagonal, like that? No. It's only going to slide along the table, one way or the other. Therefore, hypothetically, if it does have an acceleration, the acceleration is going to be along the table and 0 perpendicular to that. So along the table, nothing perpendicular. How should I choose what I call X and Y? If you can, choose X and Y so the acceleration only points in one direction. So in this case, I know the only possible acceleration is along the table. So I want to choose X and Y so that it points parallel and perpendicular to the table. So I want to choose X and Y. Tipped up. And the reason is because that lets me say that the acceleration in the y direction is 0. So I'll have some equation, blah, blah, blah equals 0. That's easier to solve than blah, blah, blah equals something even uglier. Right? If you choose parallel and perpendicular to the ground, you're going to get gross. I promise you, don't do that. This is the way to go. And I personally, just so I don't get confused, and I always do it the same, I define positive x to be up the ramp. Whether the ramp is to the right or left, I just always say positive x is up the ramp, and then I never have to think about it again. I just always do it the same. You can do it if you want. I would just suggest not reinventing the wheel every single time, just have a routine. So I do up the ramp is positive x, down the ramp is negative x. Okay? All right. So, very good. Now, if this is x and y, which are the forces that are already aligned with the axis? Choice. Well, F is already, friction's only in the x direction, because x is along the table. Tension is in the x direction, because it's along the table. Normal force is perpendicular to that in the y direction. So friction, tension, and normal forces are already aligned with the axes that I've chosen. The only one that requires any trigonometry is the weight. Okay? If you choose parallel and perpendicular, you're going to get trigonometry with friction, normal force, and tension. And that becomes more complicated. So, all right, so we want to break the weight into components which are parallel and perpendicular to the table. So here's how you can go through this with trigonometry and stuff. Side, opposite interior angles and vertical angles and all that. Actually, we can just do that. I've already marked it on the board. That's how easy. These are vertical angles, right? You have two lines which cross, which means the angles on opposite sides of the vertex are equal. Here's the other way I like to do it, which is more kind of physical. Here's the floor, and here's the table. And as I change the angle, you see that this angle scissors to 0. Yeah? And everything's rigid. So if I twist this, the diagram is going to twist by equal angles. So if you can follow the angles and figure out which ones scissor to 0 as you flatten the table, they have to be the same. Right? So if I think about it, the weight is always going down, but this normal force is going like that. As I flatten the table, this top angle scissors to 0. So therefore, this top angle must be the same as this angle, which is the same as 30. So when I look at it, if I have a diagram, then I use vertical angles, fine. But if I walk into just a room and I see, oh, as you change this, something happens over there, and I'm thinking, how do I know? Well, then I just start saying, okay, well, if I imagine things are like scissors, kind of going to 0, as I change this to 0, what else goes to 0? They're probably the same. So that's kind of a more physical way to do it. So this is going to be 30 degrees. Therefore, the weight is minus mg. This is opposite 30, so this is going to be minus mg sine 30. This is going to be adjacent to 30. It's going to be minus mg cosine 30. Okay? Okay with that. All right. Now, let's draw my force diagram. Forces, X and Y. I have weight, normal, tension, and friction. Okay. In the X direction, does the weight point in the X direction? Yeah. Now, because the X direction is parallel to the ramp, there is a component of the weight which is parallel to the X direction. This is minus mg sine 30. Sine of 30 is a half. Okay. In the Y direction, I get minus mg cosine 30. Cosine of 30 is 0.866. That's why I use 30 degrees, because it's easy to do the trick. Okay? All right. Now, the normal force is only in the Y direction, and I know it's positive. The tension is only in the X direction, and I know it's positive 20. The friction force is in the X direction. I just drew it like it was negative downhill, but I don't really know. So I'm just going to call it F, and I'll do the math. If it comes out positive, then it's uphill. If it comes out negative, it's downhill. I don't just make a guess. Just call it F. But we're going to assume it's static friction. So we're going to assume it's static friction. We don't know that. We have to guess and check. Lots of guessing and checking. But we do know there's nothing there. Okay? So the logic is we assume static friction, figure out what static friction is needed, and then compare that to the maximum possible static friction to see if that's really true. Okay? I add these up. So I get normal force minus mg cosine 30 equals 0, because there's no acceleration perpendicular to the table. Therefore, normal force equals mg cosine 30. And if I'm thinking about this, cosine 30 is 0.866. G times that's about 86.6. 8.66, and then the mass was 5, so I should do 86.6 cut it in half, 43.3. Ballpark. Have a calculator. Is that that close. Five times 9.81 times cosine of 30. 42.5. That's rounding things too much. 42.5. All right. If we assume it's static, I add these up and they better equal 0. So that means so I get 0 equals f sub s plus 20 minus mg sine 30. So that says 0, I'll just solve it. Say f sub s equals mg 50 is about 25. Negative 25 plus 20 in round numbers. So it's about negative 5. We should, I'll do it here. It's about negative 5. So I'll do 20 minus 5 times 9.81. Okay, so negative 4.525. Okay. All right. We assumed it was static friction. And the amount that we need is negative 4.5 newtons. We have to check that that's even possible. How do I figure out the possible amount? Well, I do mu sub s, 0.2 times the normal force. Then you can't use the old normal force, you have to use the new normal force because it's a new situation. So I do 0.2 times 42.5, and I get 8.5. So check f sub s is less than or equal to, question mark, f sub s max. Well, this was 8.5, whereas this number was 4.5, the magnitude. So, yes. So it doesn't slip. It's static, nothing moves, and that's it. What does the minus sign tell you? What does the minus sign tell you about the static friction? Well, remember, I mean, I know I drew it this way, but we didn't assume positive or negative when we did the math. So if it had come out to be positive, it would have been up the hill. So the friction would be helping you go up, holding you up. Whereas here, it turns out, friction is still pulling you down, it turns out. I don't know. It's hard. It is what it is. Okay? So the minus sign tells you the direction of the friction force here, and it does remain static. If this number had come out to be 10, I don't know. Well, it would have been like before. Oh, fails the test, Dahl's kinetic, resolve. Do it all again. So these problems, I don't know. I don't think of them as hard. I think of them as big. There's just lots of this and that to check and check it. Okay, we're about out of time here. So we got 10 minutes. 10 minutes. That's okay. So there are some questions like this on the sapling assignment. There are also some questions on drag force on sapling. Okay, so drag force is really a type of friction, but it's friction between an object and a fluid, as opposed to dry friction between objects sliding over each other. So because its behavior is so different, we just give it a different name. We just call it drag force, even though microscopically they're the same. All right, here's the deal. Drag force. If I give you, let's do a test. I've got a piece of paper here. I'm going to give it to someone. Make that, I want you to let go, make that object, that piece of paper, have the biggest possible acceleration. Ready? Go. Oh, that wasn't very big. Let's try it again. Can somebody else do it? Now you can do it. Think about what else could you change? Yeah, I didn't tell you. You can do whatever you want. What can you do to make the acceleration bigger? People online, I'll show you here in a minute. Oh, she's going. All right. That'll work. That'll work. She's making a paper airplane. That'd work too. I was going for this. But, you know, point taken, right? Compare that acceleration to that acceleration. There's clearly a difference. So wind resistance has different variables than dry friction. I'm going to give you the formula for it. So wind resistance opposes motion, so drag force. Drag or wind resistance opposes motion. Okay. And so it turns out, you know, it depends upon lots of things. Roughness of the surface, obviously the shape matters because we got different results just by changing the shape. The thickness of the fluid, like the density of the fluid, right? If I do something in water versus air, you should get very different results, okay? More drag in water, just because there are more molecules bouncing off something. You know, as you try to pull something through water, it runs into all these molecules, slows down. You pull it through air, it's just occasional collisions, so therefore there's just less. Okay? All right, so the formula for the drag force. So the symbol I will use is D for drag force. Again, it's just the magnitude. You have to look at the scenario, the picture, to figure out the direction. It opposes the velocity, so it points opposite the velocity. And it equals, so conventionally, people put in a half. There's a reason for it, but it's just convention. Okay, half. There's a number called the drag coefficient. And I think Sapling uses the Greek letter capital gamma. The book, I think, uses the letter C with a D, which makes more sense to me, so I can remember for drag. It's just the drag coefficient, but the Sapling uses gamma. Half of gamma, and then so you have to kind of imagine you have some sort of irregular object with some velocity like that, right? Imagine like it could be a a lumpy, deflated basketball moving through a pool. Okay? What you should imagine is that there is a sort of a cross-sectional slice, the biggest possible cross-sectional slice, and it has some area. So this is the area of the cross-section. Not this total surface area, the area of the, it's kind of like the image of a shadow, or the area of the shadow it would cast. And that's the way you should think of it. Just the area of the shadow it would cast in the direction of the velocity. So the bigger that is, the more drag force you get. Okay. Times the density of the fluid. So it could be the density of air, which is 1.2 kilograms per meter cubed, or it could be density of water, which is 1,000 kilograms per meter cubed. I know you guys are chemistry, I'll tell you it's 1. That's in barbaric units, gram centimeter cube. Oh, yeah, that 1,000 kilograms per meter cubed is the density of water. Whatever the fluid is, it's going to be there. Times the speed squared, the velocity squared. So you do the magnitude of the velocity squared. Okay? You know that. If you've ever put your hand outside a window as you go down the highway, you know that the drag force changes as you rotate your hand. That's because you're changing the cross-sectional area. Your hand is like this, it's really small. The shadow your hand casts is really small in the direction of the velocity. You do this, it's big, so the drag force grows. The other thing you notice is, if you're just going down your driveway, the drag force is very small. You only really notice it once you get up to whatever, going down the street, right? And then it grows. So it grows with a velocity, actually goes like a velocity squared, turns out. That squared part is kind of the hallmark of drag forces for small velocity. Okay, that's the formula for drag force. There's another force you might have heard of called viscosity. You heard that before? It's kind of qualitatively similar, except it actually grows with linear velocity. I don't think we have any homework problems on it, so that's why I'm not really emphasizing it. For us, it's just some other force that has a different formula. When you use it, they have to give you all these numbers to plug in. One thing I will point out, I want you to watch what happens. I'm going to let go of this paper, and as it falls, at first, it's kind of steady motion, and then it kind of gets irregular. Don't worry about the irregular stuff. Focus on that very first bit of steady motion. When I let go, what does it do? The very first bit, I let go, it starts to speed up, right? It accelerates down. But then after a very short amount of time, doesn't it look like it has a constant velocity? It does. That's called terminal velocity. Terminal doesn't mean you die. Terminal means constant velocity. It's the final velocity. So what happens is this. Imagine you step out of a hot air balloon. Plank. Hot air balloon. Okay? So, but you have your own parachute, so don't worry. I don't know, whatever. You have an umbrella. Good luck to you. Okay. So the minute you step off, okay, what's your velocity? That very first instant, you just step off. You don't even jump down or jump up. You just step over. Your initial velocity is 0, right? So at that very first moment, how much is the drag force? 0. Okay. So at the very beginning, there is no drag force. You just have gravity. It pulls you down. You start to speed up. You accelerate downwards. You go faster and faster and faster. As you go faster and faster and faster, now the drag force grows and grows and grows and grows. And drag force opposes velocity. So if you're going down, the drag force is going up. So you end up in a situation where your free body diagram is like this. Drag force and weight. And the faster you go as you fall, the weight never changes. It's always minus mg. But this thing grows and grows and grows and grows and grows. Eventually, start off at 0. Eventually, it becomes equal to your weight. And opposite, equal and opposite. At that point, the net force is 0, which means the acceleration is 0, which means your velocity becomes constant. So terminal velocity is when your drag force equals the weight force, and they cancel out, and you just coast. You just fall at a steady or at a constant velocity. It might be a big number, like for us it'd be terminal in both senses of the word, but it'd be the same. All right. So in that case, you would say, so the problem will be find the terminal velocity. That'd be a typical kind of problem. You would say, oh, terminal velocity means drag force equals, or terminal velocity means the acceleration is 0. So this means acceleration equals 0, which in this case means drag force equals mg. So I just solved the problem and said, okay, 1/2 A times gamma times rho, the density of the fluid, times the velocity squared is mg. Turn it around and you get the velocity equals 2mg over A gamma rho, take the square root. Just some formula. And this is the formula for terminal velocity. Okay, so there's some sapling questions where you're using that idea. It's mostly, you just need to know the formula. You just use it, and just the definition of terminal velocity. It means you're just constant velocity. It just never changes. Okay? So gravity treats all objects the same. But the drag force does not. It changes as you change the shape of the object, and the mass of the object is going to matter too. So in reality, in this room, if I drop a penny and a feather, the penny has a bigger acceleration. We know that. Whereas just gravity alone in vacuum, they would tie. It's a drag force that counts for that difference. I don't know, some of you guys in chemistry, you might talk about viscosity. The formula for viscosity is very similar. It has the density of the fluid, the area matters, it's linear here, and then the coefficient's a little different. One other thing, I think sapling even specifies, does this. For most everyday things, gamma is pretty close to 1/2. So in one of the equation problems, I think sapling just gives you a formula, and they don't write gamma even, they might just write 1/4. It's just, they're using the fact that for normal things, this is commonly 1/2. It's a good estimate. Somewhere between 0.4 and 0.6. So sometimes people just simplify it that way. All right, I'm over time, so I gotta stop. Okay.
They're all gone.